Hi everyone, I'm Tong, and I'm presenting our work Inducing neural collapse to a fixed hierarchy-aware frame for reducing mistake severity. This work is done by me and my supervisor Jim Davis in the Department of Computer Science and Engineering at Ohio State University. Neural collapse is a recently discovered phenomenon such that during training of a network, its penultimate features are collapsing to their intraclass means. Their intraclass means and the associated classifier weights are collapsing to a simplex equiangular tight frame, abbreviated as ETF. Since we observed such collapse would occur, one could fix the classifier at ETF from the start of the training and facilitate the collapse of penultimate features. Comparing to hierarchy-agnostic ETF, our proposed HA frame is hierarchy-aware. On the left column of the figure, you can see that all leaf classes are equally apart from each other in ETF. For example, class A is equidistant to class B, C, and D. On the contrary, our hierarchy-aware frame, or HA frame, encode hierarchical relationship into pairwise cosine similarities between the classes. This allows us to insert prior knowledge of the desired class hierarchy. For example, class A could be closer to class B than to class C and D. For a given hierarchy of classes, we first represent their class relationship by the following hierarchical distance, which is the height of lowest common ancestor between the leaf classes. Then we map the hierarchical distance to cosine similarity via an exponential function. This function has one hyperparameter, gamma. On the right, we have a figure showing you the influence of gamma. Larger gamma will map closer classes further apart from each other. We also need to search for a proper lower bound, S-min, to ensure the resulting cosine similarity matrix S to be positive definite. Once we have the desired cosine similarity matrix, we can treat it as a product of fixed HA frame classifier weight matrix times its transpose. This can be further decomposed with eigenvalue decomposition. And because S is positive definite, we can apply square root on its diagonal matrix D of eigenvalues. U in this formula is an orthonormal matrix acquired from QR decomposition of a random matrix. This allows a random rotation. Therefore, we have our HA frame W in the end. This is the architecture overview of our approach. We can work with any modern neural network backbone. We just add a 1x1 convolutional layer to adjust penultimate feature dimension to the number of leaf classes and a transformation layer with residual connections to facilitate the collapse. And in the end, we fix the linear classifier weights at the HA frame weights W we found in the previous step. Our approach uses a hybrid loss of cross entropy and cosine similarity with a tunable mixing ratio alpha. We mainly evaluate our approach and related works with three types of metrics. The first one is top one accuracy. The second one is average mistake severity, which is the sum of heights of lowest common ancestor between incorrect prediction and their ground truth, then average across all incorrect predictions. Lastly, we have average hierarchical distance at k. This is averaging hierarchical distance of top k predictions to the ground truth for each example, then average across all evaluating examples. We can see that on both large datasets, our approach demonstrates improved performance compared to the recent works. Finally, we evaluate the neural collapse quality of ETF and HA frame with the following two metrics. Angular collapse examines whether the cosine similarity of penultimate feature means or classifier weights are reaching the ideal cosine similarity. Self-duality examines if the penultimate feature means are collapsing to the classifier weights. For both metrics, smaller value is better. As we can see in the figures on the right side, both metrics are approaching zero as training with more epochs, which shows that they are approaching the neural collapse. In summary, it's easy to adapt our approach to different hierarchies. Our approach provides an analytical solution to HA frame and offers a new route to reduce mistake severity from neural collapse point of view. For more details, please check out our paper and code. Thank you for watching.